So now let me start with what is quantum error mitigation. So the best way to understand error mitigation is to compare it with standard quantum error correction. So in standard quantum error correction, one typically encodes logical qubits into many physical qubits, then performs intermediate measurements to detect errors, and finally, actually, as soon as you detect an error, you apply a recovery operation. So this is very nice because it's scalable. In principle, you can obtain a fault-tolerant quantum computer in this way. This is a very important and actually well-established result of quantum information theory. On the other hand, it's very hard to apply with near-term quantum computers because it requires a lot of qubits and classical control. What is instead very easy to apply with the computers that we have today is error mitigation, which can be considered as a kind of compromise between not applying error correction at all and the ultimate goal of error correction. So in error mitigation, actually, instead of correcting errors as soon as they happen during the computation, what you can do is that you run a set of multiple and different noisy quantum computations, which are related to the computation that you want to implement. Then you collect all the results, and then you infer, given all the noisy results, what could be the ideal result that you want to extract. And this is, unfortunately, asymptotically not scalable in the sense that at some point, for very long circuits and large number of qubits, the cost of error mitigation is exponential, but for near-term quantum computers, it can be still very, very useful and give a good reduction of the error.